So, welcome to the bonjour pour cette nouvelle session et nous avons la chance d'avoir des élèves du lycée Żmichowska à Varsovie et ils sont 9 qui vont nous présenter leur travail de recherche sous le titre ENI Games et probabilité. Donc, ils vont parler en anglais and I give you the word. You have 10 minutes to present your work and then you will have some questions. Thank you.
We are the students from High School of Nazi Żmichowska in Poland, and for this school year we worked on a project ENI game. The subject was given to us by Marcin Moszyński from the University of Warsaw. Our task was to find the probability of winning the game. I would like to present our students now. So, Paweł Furmański, Marta Krzywdzińska.
Hi, hello.
Magdalena Mikiel.
Hello.
Marianna Ninigodzi.
Hello.
Anna Piskosz.
Hello.
Marta Skorupa.
Hello.
Bartosz Trzosiński.
Hi.
And me, Kinga Słomińska. There are two players in the game. The first one hides the treasure. The second one has searches for it. The first player chooses a tile under which he hides his treasure. Then the second player indicates where he thinks the treasure is. When that's done, the first player covers a tile that is empty and non-indicated. Finally, the second player can decide if he changes his first guess or not. If he decided to change it, he can choose another tile only when the tile he chooses is not covered by the first player. If the second player in his last guess indicates a tile with the treasure, he wins. Otherwise, the first player will be the winner.
So, for your better understanding, we prepared a short film from Scratch program showing the process of the game. So, the light green tile is the first choice. The red tile is the tile that is covered. And as we can see, the player decides to change her choice. So the dark green tile is the second choice. And the game was lost because the treasure was on under the tile number 1. Yes, we hope it's a little bit more clear now.
Problem concerns the question, which choice is better for age, keeping the choice or not? To solve the problem, we started by playing the game a couple of times. We played both strategies, when the second player changed or not his decision. We wrote down our results and basing on them, we counted the probability of winning. By comparing our results, we could calculate mathematically the probability and come up with a formula. While playing the game, we decided to try different numbers of tiles. Unfortunately, we played not enough games for satisfying results. Even then, we could notice that changing the choice of the second player gave him more chances to win, no matter how many tiles there were.
We programmed Excel so to speak. We programmed Excel so it simulates the games. I'll shortly try to explain our Bayesian simulation for N5. The treasure is always on the first tile, as the column F shows. Column G is responsible for picking the first choice, which is tile from 1 to 5. From H to M are only assistant columns that help to pick covered tile. Column N picks covered tile basing on information taken from the previous ones. Again, columns from O to S are only assistant columns that help to pick the final choice, which we can see in column T. Column U checks if there was change of choice, and column V checks if the game was won. The results are gathered and showed as winning ratio in both situations, so with change or without change. Here we can see examples of gathered results for a different variance of N. For N3, winning chance with changing first choice is equal 70%, and chance of winning without changing choice is equal 37%. For N4, winning chance with change is 40%, without change 25%. For N5, winning chance with change is 29%, without change 17%.
We have created the ENI game in the Scratch program in order to see if the results were different from our Excel games. We have run a vast amount of games with different value of n to compare. Scratch simulation gave us following results. For n equal 3, winning ratio 63% with change and 32% without change. For n equal 4, winning ratio 36% with change and 24% without change. For n equal 5, winning ratio 30% with change and 18% without change. Comparing results from Scratch to results from our Excel simulation showed that they are very similar to each other, making our simulations valid.
We decided that the best way to check mathematically the probability is to use a graphic method. It allowed us to calculate the probability of winning when we change our decision with a given n.
With the help of our teachers, we finally managed to draw the diagrams. Here is an example with 3 tiles. The treasure is hidden under the tile marked as T. There are 3 tiles to choose from, and that makes the probability that the searcher picks the tile with the treasure first 1/3. Since we took into consideration only the scenario where the searcher changes his first choice, if he chooses the tile marked as T, where the treasure is hidden, first, he will lose, because it means that he will pick either tile 1 or tile 2 afterwards. However, if his first choice falls on tile 1, there is a 100% chance that he will win the game, because after the searcher chooses tile 1, the hider can cover only tile 2, making tile T the only choice available. The same applies for tile 2. To calculate the probability of winning, we need to focus on these 2 winning scenarios, which on the diagram are marked as ending in a plus. We have to multiply 1/3 by 1 2 times. The result is 2/3.
We applied the same logic to diagrams when n equals 4. We calculated the probability of winning in the same way. The result was 3/8. We did the same calculations when n equals 5, and the result was 4/15.
After all of our calculations, we came up with a formula. It allows us to calculate the probability of winning when n is not determined. We then compared it with the results of our games from Excel and with our Scratch simulation results. The calculations were quite comparable. The results led us to find a better formula that includes k, the number of covered stones. We compared the results of our games with Excel simulations for when k equal 2, and they turned out to fit our calculations.
We wanted to find out which is better, changing or not changing your choice in the game. We played the game, but it wasn't enough, so we did more research, such as simulation in Excel and Scratch, drawing tree diagrams, and came up with a formula. We came to the conclusion that if n equals 3, the probability to win equals 2/3 when we change our first decision, and 1/3 if we don't.
When we were increasing n, we noticed that this is not changing the proportions significantly, and the chance of winning is always greater when we change our first decision. We studied that only for the K1 and partly for K2, so we encourage you to check what happens when the number of K will be higher. We would like to thank you all for listening. We hope you enjoyed and learned something new. We would also like to thank our teachers who helped us and guided us through the project. And I guess now it's time for questions, if there are any.
So thank you very much for your presentation, which was very clear. I look at the chat to see if there are questions, and I do not see. I do not see a lot of questions, but perhaps I do not look at the chat very well. Be sure that your presentation was very clear. It's perhaps the reason why there are not so many questions. And when you work on this question, you have said that you have a word for k equal 1, k equal 2. And do you have some idea about how the problem could evolve with other values? As someone wants to answer? I have a question for you that is on the chat. Can you explain again? I am asked. Could you explain again how the construction of your tree? Because someone didn't understand very well the process of construction of your tree. Beginning with a simple case, the case with n equals 3. Okay? Who wants to speak? Who want to take the word and answer the question? You have all your microphone muted. Who wants to open the microphone and answer?
So I can try to explain the
choice. Okay, thank you very much.
Because we try to use the like the calculation of probability. We try to visualize the probability with using the trees.
Yeah.
And in this example, like every tree is like different decision that can be possible to make by people playing it. And it allows us to calculate the possibility for winning or losing in certain situations and scenarios. And like, for example, here it shows for n equal 3. So there were like 3 squares in the game.
Yeah.
And we did the same for the other examples. And mostly we use the trees to visualize our calculations. And they're based based on the calculation of probability. I forgot how it's called in English, unfortunately.
Yeah.
Like this specific calculation, but it was used to do so.
Okay. I have another question on the chat. Have you tried some variations on the rules of the game? For instance, with several hidden treasures.
Can you repeat several different treasures?
Yeah. If you have new rules for the games, for instance, with several hidden treasures. Have you tried this kind of thing?
No, we didn't try it. We tried different numbers of Ks. So
Yeah.
The second player could choose another tile 2 times, but we didn't try different numbers of treasures. Okay.
So do you plan to go on with this problem now after the Congress? I hope that you will. Do you plan? I suppose that you plan to write an article for MATH.en.JEANS and propose it.
Yes, we're writing an article. It's almost done, I think.
Ah, okay, thank you. Very nice. So I think that if there are no more questions, we will stop now, and I congratulate you very strongly because your work and your presentation were really beautiful, and your work is excellent. Thank you very much.
Thank you.